is almost tight additive guarantees for KH connectivity. So this is about a fundamental network design problem called the KH connected subgraph problem. So let me dive in and uh, and start by defining the KH connected spanning subgraph problem. So the problem is quite simple to state. We're given an undirected graph, some costs on the edges, non-negative costs on the edges, and some integer k. So here is a graph. The numbers labeling the edges are their costs. I haven't labeled every edge, but you can think of the unlabeled edges as having cost 1. And k is equal to 3. And what I want is a min cost subgraph that is kh connected. What is kh connected? It means that we want kh disjoint paths between every pair of nodes. Or equivalently, you can formulate this in terms of cuts, that every cut has to have size at least k. So that's the definition of the problem. So for instance, here, this is, I think, a solution, although I haven't really checked. But for instance, between these two nodes, there are these three edge disjoint paths. Okay. So, and there's a close variant of this problem, which is the spanning multigraph problem, where the only difference is that we are allowed to buy multiple copies of an edge, right? So the solution can be a multigraph, right? So let's make sure that we are sort of on the same page here. So the one edge connected spanning subgraph problem, we all know what that is. That's the someone speak up. That's the minimum spanning tree problem, which we know can be solved in polynomial time. But for every k at least 2, these problems are NP hard, and in fact APX hard, which means that we can't approximate them better than some constant. Any questions about the definition of the problem? Okay, the entire talk is about this, so it'd be good to clear any confusion about that. Okay, so to place our results in context, I want to go over some background into this problem. And I want to sort of talk about this background by looking at this 2D plot where I have edge connectivity on the x-axis and the cost, the ratio of the cost divided by the optimum on the y-axis, right? So the problem is NP hard, so which means that we can't hope to get the optimal cost, I mean a feasible solution, which is KH connected, and the optimal cost, right? Good. So, I mean, usually in approximation algorithms, what we do is we want to find a feasible solution, of course, within some factor of the optimum. And so what's known about this is that, so since the 80s, by work of Fredrickson and Yaya, we have a two approximation algorithm. And I've also cited Jen there because, I mean, we'll be using some of his ideas, but Jen solved a much more general problem, which also gives a two approximation for this problem, right? So that's the best known in terms of approximation algorithms, right? Closing this, I mean, improving upon this too is a major open problem. But very recently, so there's a in 2024, Hershkovitz, Klein, and Zenklusen gave an alternate kind of guarantee where they showed that well, we can get cost at most the optimum, but we can violating the connectivity requirements, right? So we can get k. They showed that you can get a k minus 10 edge connected solution of cost at most the optimum. All right. So now this sort of opens up a new maybe line of investigation that if I wanted to sort of stay below this 1 here, how close can I get to k? Again, I can't get k, but I can get. I mean, I can hope to get k minus 1. Right? And that's what we get. No, this is a lie, right? So I mean, otherwise it wouldn't be almost tight. So this is open. So I can't sort of promise you the sun, but I can promise you the moon. What we can do is we can, for k even, we can get k minus 2 edge connected, which implies that for k odd, we get k minus 3 edge connected solution. Right? Of course, it moves the optimum. And the other thing that that we also show is that you can get better than 2 approximations, so 1.5 approximation, and get a k minus 1 edge connected solution. Okay, so that question mark is still sort of a very interesting and I guess somewhat vexing open question, but that's, I mean, that would be the tightest guarantee. Yeah.
Here, like at what regime these results become? Like K minus, like how much should we go to the left of K minus 10 before these results become easy or three?
So the Jans thing or the two approximation can also be used to imply that you can get k by 2 at cost post the optimum, because you can sort of scale things, the LP solution, by a factor of 2. Sorry, yeah, I'm jumping ahead a bit, but these are LP relative guarantees. You can scale the LP solution, you can get kind of k by 2, assuming k is equal.
But even that requires some the standard NC.
Okay, so for this KH connected thing, I mean, the Fredrickson and Jaya thing is combinatorial. You can kind of solve directed arborescence and get that.
But your graph is on there.
The graph is undirected, right? But one way of getting this is that you can bidirect edges and then solve a directed problem. Okay. Good. Any other questions? So let me mention another similar kind of graph. So people also look at, and very recently there was a independent of our work by Newtov and Cohen in ESA 2025 that using the same techniques as Hershkovich et al., but refining, but I mean, sort of a more clever or careful accounting, they showed how to get K-4 edge connectivity. Right? So there is also work on this problem in the unweighted setting where all edge costs are 1. And there you can get much better approximation guarantees. You can get guarantees of the form 1 plus some constant divided by k. And the state of the art is like roughly a 1 plus 2 by k approximation, feasible solution, so kh connected solution. And our 1.5 approximation actually translates to this 1 plus 1.33 by k approximation guarantee, but losing 1 unit of edge connectivity. All right, so let me just state these same results again, but maybe in a more easier to parse form. So as I said, so we give a polytime algorithm. It outputs a subgraph that has cost at post the optimum and is k minus 2 edge connected for even k, and for k odd k it's k minus 3 edge connected. All right, and C of h is just a shorthand for the sum of the edge costs in my solution. These cost bounds are with respect to the optimal value of the natural LP relaxation for the problem, which I'll show in the coming slides. Again, I already said this. I mean, k minus 1 would be tight if you wanted cost most the optimum, so this is almost tight. And I think the main improvement over this Hershkovich et al., I mean, besides the guarantee, is that our algorithm is actually and clean, both in the description and the analysis. And I hope to get that across. I'm hoping that I can sort of cover pretty much the entire algorithm in the analysis. And the other thing that we get is 1.5 times the optimum, but k minus 1 edge connectivity, which also gives some bounds for the unweighted problem. These results for KH connected spanning subgraph also imply some result for the spanning multigraph problem, where we are allowed to buy multiple copies of an edge. So there one can get a feasible solution, but the cost is slightly larger than opt. So it's either 1 plus 2 by k times opt or 1 plus 3 by k times opt, depending on whether k is odd or even or odd. And that's just a very simple argument. So let me just show it here. So basically what you can do is you can write down the LP relaxation for the KH connected spanning multigraph problem. So I have a variable XC that tells me how many copies of an edge we are picking. I am allowed to pick an arbitrary number of copies, so there's no like upper bound constraints. If I were in the edge connected spanning subgraph problem, I would include XC less than equal to 1. And these are just the cut constraints that say that you have to have at least k edges, allowing for multiplicities across every cut, right? So to get from the KECSS results to this problem here, all we can, so let's say LP star is the optimal value. So say K is even. What I can do is I can just take the optimal solution where instead of K, I have K plus 2 in the constraints. And I can just view that as a solution to the spanning subgraph problem by just making, in the input graph, I just make enough parallel copies of an edge so that if they were sort of, if XE was like 5.5, I'll create 6 copies and I'll say the first 5 copies have value 1 and the sixth one has value 0.5, right? This is just a simple trick to kind of translate this to a solution in this graph for the KH connected spanning subgraph problem. Okay, and I can always do this, right? And now I can use the result for KH connected spanning subgraph. So I had K plus 2H connectivity in the LP solution. I lose 2, so I get KH connected. And the cost is at most the cost of the optimal LP solution here, which is at most the cost of this X star solution, which was the optimal solution for this K plus 2 ECSM. But the thing about this ECSM problem is that, I mean, basically, if you have the solution for any K, right, by scaling it, you get the optimal solution for any other K prime, right? So this one is just K plus 2 by K times the optimal solution for the problem with K. Right, so here, this has got nothing to do with how we obtain this guarantee, right? Anytime you have a guarantee for the edge-connected spanning subgraph problem, which is LP relative, you can always do this translation. Okay, and some other results that we obtain is that, so you can look at the degree-bounded version. Yeah.
The graph version based on this, why won't you then just pick a minimum spanning tree and then just rescale by K?
Yeah, so I mean, that would be a feasible solution. Like you can always take a MST and take K copies of that. That could be twice away from the optimal. Like if you have a cycle and K is equal to 2, then picking 2 copies of all but one edge could be twice away from the optimal. Okay. Yeah. Good. Yeah. But indeed, the LP solution would just be K times the solution for K equal to 1. Yeah. Yeah. Good.
So the other minute is 2.
The integrality gap is 2, yeah. I mean, well, so yeah, I mean, for K equal to 1, it's 2, but then for larger K, you can get this. I mean, the integrality gap decreases as a function of K for this problem here, which kind of makes sense because, I mean, although in the LP solution, you're sort of multiplying things by K, right? A lot more things could become like an integer plus some fraction, and the integer part you get for free then. Yeah. Good. Yeah. So feel free to interrupt me at any point with questions. I mean, this should be an easy talk technically. I mean, that's sort of one of the features that I want to highlight. So I mean, I have plenty of time, I hope. Okay. So we also studied the degree bounded versions of these problems where we want again the same kind of the solution with the same connectivity properties, but now you could impose no degree lower and upper bounds. So this is there has been work that looks at degree bounded network design problems, more general network design problems. And for this, essentially using the same ideas, one can get the same cost and connectivity guarantees with an additive violation of roughly 2 on the degree lower and upper bounds. Right. So this kind of falls out as a byproduct of how the guarantees are obtained. Right. And prior work basically gets guarantees, which is like twice the optimum. You get a feasible solution in terms of connectivity, and the degree bounds are violated either by a constant multiplicative factor or by, in this case, an order K additive factor. If you have any questions about this prior work, you should ask Lapchi. He's the expert on this. Okay, so I want to talk about basically my plan is to cover this result here. So in the rest of the talk, I'm just going to assume k is even, right? As I said, for odd k, we just work with k minus 1, so that immediately, so odd k will follow immediately from even k. And I want to try to get across essentially everything that's involved in this result here, the first result here. Okay. Okay, and to do that, I want to start with Jain's iterative rounding algorithm. So Jain, in some seminal work, gave a way of showing how to use LPs for much more general problems, the survivable network design problem, where you can have different connectivity requirements between pairs of nodes, right? I'm just going to look at, specialize that for the KH connected spanning subgraph problem. So what is Jain's algorithm? So we look at the LP relaxation of the problem. This is the same LP that I wrote before. Again, I have now XC less than or equal to 1 constraints. Instead of sort of explicitly writing down K there on the right-hand side, I'm going to just put, I'm going to say that the right-hand sides are given by this function f. Initially, that function is just going to be K, but we are going to be, we'll have an iterative algorithm where we're going to gradually pick some edges. As we pick some edges, we may need to cover sets. We may need fewer than k edges on the boundaries of some sets. So that's why it's useful to have this f of s notation. Okay, so we find an extreme point optimal solution to this LP. What is extreme point? So, that picture is supposed to indicate what an extreme point is. It's like the LP feasible region is some polyhedron, and we are looking at a corner point of that feasible region. Right? So every extreme point is defined by its tight constraints. If I set all the tight constraints at that point to equality, that uniquely defines the point, right? That's an extreme point. What one can show for these kinds of network design problems is that, so the tight constraints here come from some sets, those cut constraints, and from some edges which are set equal to 1. The set constraints could be, you could have an arbitrary collection of sets a priori, right? But what is kind of known is that you can take the tight set constraints and go from sort of an arbitrary collection to a much more structured collection of tight sets called a laminar family, right? So a bunch of things here. So tight set means that the constraint there is tight for the set. Laminar family means that it's structured in the following way. Any two sets are either disjoint or one is contained in the other. All right, and by defines this extreme point, it means that, well, if I look at the support of this extreme point solution, then that's completely defined by setting the sets in the laminar family, setting those constraints to be tight. And we also have to account for the integral edges, so setting those constraints as well to be tight. Right? The unique solution to the system is X star, right? The non-zero portion of X star is the unique solution to the system. That's what I mean by this laminar family defines X star. Okay? And this is sort of a well-known idea in network design problems. I will get to how we can get to this, right? But let's continue with the flow here. So we get this laminar family, and then the key insight of Jain is this sort of very nice property that from this structural property leverages that to show that there must be some edge whose value is at least a half. Right? This was his key insight, right? And so once we have that, what we can do is we can pick this edge and we can update now that f function, all right? So that f function was capturing how many edges we need on the boundary of these sets. Once we pick some edges, for some sets that may go down to below k, and it'll keep going down. So we update this and now we iterate. And we keep doing this until we get a feasible solution. And this is, it's easy to see that this is going to give you a true approximation, because the only time where we sort of did something suboptimal, right? We took something that was at least a half and we picked that edge now fully. So we lose a factor of 2, right? So That's why you get a 2 approximation.
So I'm confused. Once you remove the edge, why does the opt make an improvement? Like you sound saying that f of s minus 1, this new problem, opt also has decreased by half the 1.
Right. So good. So if I look at the other edges, right, the edges other than this, they still give me a feasible solution to this new problem here. Right? Because
so it could have gone even lower, but
at least it decreases by the cost of this edge. We are picking this edge to an extent of, yeah, okay, good, yeah. Sepper is making sure I'm not pushing something in the cracks, yeah.
So
Question.
it's possible that I would be empty set, right?
It is possible that I could be the empty set, yeah. So this is, I guess I introduced the notation just to make precise what I mean by defines X star, yeah.
The function f is general, linear, or?
So that function f, I'm just looking at KH connected spanning subgraph. So that function f is initially that function there, where for every non-empty set other than the entire node set, it's k, and then it gets updated down. Okay, yeah. So I'll get to that. Yeah. Okay. Good. Okay, so this is Jen's work, right? Now, so this gives a 2 approximation, gives a feasible solution. Our goal is to get cost at most the optimum, but we are allowed to relax the connectivity constraints, right? So the iterative nature here is that just we are picking edges iteratively. In later work by Lapchi and others on degree-bounded network design, right? They introduce sort of another way in which you can make progress in an iteration, namely that you could potentially drop some constraints, right? And so that kind of gels well with our goal because remember, we are not targeting feasibility, right? We are targeting almost feasibility, right? We are allowed to only settle for a k minus 2 edge connected solution. So that's, we are going to just make the simplest modification here. So we are just now going to retain the constraints for cuts that still need to be like mostly satisfied. So if a cut is already crossed by k minus 2 edges, then we are going to drop that constraint. Which means, so this f was tracking how many more edges that we want. So as if that f of s value is at least 3, then we retain that constraint, otherwise we drop. So that's the change to the LP. And now what one can show is that this structural result is still true. There is still a laminar family. And now we can actually show that there's an integral edge. There's always some edge that has value 1. Right? So now again, we can pick that edge. Because we're picking only integral edges, the cost is at most the optimum. Because we retain a constraint until its value until we have at least k minus 2 edges crossing it, we get k minus 2 edge connectivity. Right? But I mean, what's something's got to give here, and like what the main work that's involved in the analysis is now proving the structural result, right? That was kind of straightforward or very well known in the earlier setting where we had constraints for all sets. Now, because we are dropping sets, we have to work harder to show that there is this laminar family. But the other part of the argument that if you have this laminar family, there is always some edge which has a large value, that becomes quite easy, right? There's a very simple counting argument that shows that, right? So in some sense, the complexity of what needs to be shown gets, this is the main thing that one needs to show. But
and like forces your hand to be 3, the technical or the counting or?
So okay, good, yeah. So this one will still be true if I put f of s at least 2. Actually, yeah, let me say that. If we put f of s at least 2, all we can claim is that this is at least 2/3, right? And that's why you get the 1.5. And things are tight in the sense that if I want to retain the constraint as long as until at least k minus 1 edges are crossed, then there are examples where you don't have an integral edge, right? So at least something different will need to be done beyond what we do, right? So that's the algorithm, right? Question?
So, like at the beginning, every F is K because you're
Yeah.
taking K connectivity, and then at some point you're iterating and then like reducing the F for that specific, like a specific subset of constraints. And then that's why that makes sense, that some of them might go less than 3, right? Like some of the F of S's might go less.
Right, because yeah, whenever we pick an edge, we have already picked an edge crossing it, so we.
And then you.
Right, and so if we have already, if the F value goes, I guess in the green thing below at most 2, then we remove it. Because I mean that cut is already sort of has the target connectivity that we want, or a target number of edges on its boundary that we want. Right. Okay, all right. So let me isolate sort of the key technical thing that we need to show here. And for that, I'll need some terminology. So the function f that I had in the previous slide, I mean just the initial f right now, where it was k or 0 for the empty set or the entire node set, it satisfies a bunch of properties. So one property is this property that if I look at the f value of two sets A and B, then it's at most this this thing on the right hand side. This property is called weak supermodularity. Now, if you look at that, you'll actually see that, well, our f actually satisfies much more, right? I mean, f value is just k everywhere. So, I mean, if I had k and k, in fact, both of those terms would be at least 2k, provided that none of those sets are empty and A union B is not V, right? And that's called a stronger property, so which we call two-way uncrossability. So, two-way uncrossability, the max is replaced by min. But you have to take care of the fact that none of these sets are empty and A union B is not V. Because f of the empty set and f of the entire vertex set you should always think of it as 0, right? I mean, otherwise the problem doesn't make sense. So the function that was telling us how many edges to pick across a boundary of a set satisfies these properties. And for even k, we can observe that the following quantity is even. So if I take the FA plus FB plus F of A union B and A and B are disjoint, then that's even. We call this even parity. And the important thing here is that actually these properties also hold after we update F in the iterations, right? So, I mean, initially these seem like trivial properties, but the fact sort of this, for instance, this property is stated in this way and not just for any two sets A and B, because we want it to hold also after picking edges. Right? If you pick an edge, then you can one can verify that this quantity would decrease by 1 for exactly 2 of those sets. Right? That's why even parity is maintained. It would not be true for any 2 arbitraries. Right? So throughout, F has all of these properties. And the sort of thing that we show is that if you have an F that has this property, two-way uncrossability, and has even parity, and if you look at a system like this, where we want the number of edges on the boundary to be at least f of s, as long as the f value is at least 3, and edges cannot be picked more than once, then any extreme point of this system is defined by a laminar family of tight sets, and there is always an integral edge. Right? That's the key sort of technical insight that drives the algorithm, right? If I prove this, then the algorithm that I had, like again, because there's always an integral edge, you can always pick that, so you get cost at most optimum because you are only dropping a set if its f value goes below 2 or below, you get k minus 2 edge connectivity, right? So this is the key sort of technical engine that one has to prove. Okay, so let's try to show this, right? Okay, and now I'll answer Mehtab's question. So let's, as a warm up, let's say we had constraints for all sets, right? X delta S was at least f of s for every set that was part of our constraints, we have this extreme point, and again, that's kind of the how you should imagine an extreme point. It's defined by these tight constraints, and Z is this fractional is the support of the solution. So what does uncrossing mean? Uncrossing means that, so again, like if you recall, the thing that made everything possible even in Jane's thing was this laminarity property. So what we are showing is that, again, they could be the tight constraints there could involve sets that look sort of have arbitrary kind of intersection, but we want to clean things up, and we want to say that whenever you have sort of a picture like this where there are two tight sets that cross, you can come up with an equivalent laminar family of tight sets. And the sort of what does equivalent mean? It means that if I look at the span of these vectors, so this is the indicator vector of the boundary of the set. So this is what equivalence means, that I can always preserve the span of my tight constraints. And that's kind of got to do with, because we still want this extreme point, right? So I mean, in an extreme point, we need to have like, if the dimension is D, we want D linearly independent tight constraints. We want to make sure that we don't lose that property. Okay, so that's, if I can show this, then from there showing its laminarity is fairly straightforward, because you can imagine that like you can take all the tight constraints, look at a pair of sets that cross and replace them by sort of keep gradually doing these modifications, right? This may not give you like a polytime procedure to get this laminar family, but we don't actually need this laminar family in polynomial time, although one can actually obtain it. And I mean, you can come up with a cleaner sort of argument that says that pick a maximal laminar family of linearly independent tight constraints, and then you can show that it'll have the right properties, right? So the point that I want to sort of convey here is that it's enough to prove this, what's called uncrossing result. If you have two sets that cross, by cross I mean that each of these regions, A minus B, A intersect B, and B minus C, A are non-empty, you can come up with a laminar family. You can uncross them. Right? So let's see why this is true. So, and let's recall this property that which was the first property that was stated on the last slide. So this property, a stronger form of this property is true for the KH connected spanning subgraph problem, but we are only going to use this property, right? So this is called weak supermodularity. So as long as the function has this property, we can get this uncrossing and hence get the laminar family. Right, so the function value of 2, if I add the function value of A and B, then it's at most the function, adding the function values of the intersection and the union, or the set differences. All right, so how can we exploit this? Let's say it's this portion of the inequality that holds. So then I can write down this inequality. So A and B are tight sets. So that's why I have this equality, and then I'm using that inequality there. On the other hand, let's draw all the edges in Z that are incident to A or B, right? So there are 6 possible types of these edges. I've sort of labeled, so these are not single edges, these are just different groups of edges, right? But if I sort of now look at this, we can just count, and we can see that this quantity can be written as the number of edges on the boundary of A intersect B plus the number of edges on the boundary of A union B plus twice the number of edges that go between A minus B and B minus A, which is what is theta. Right? And now, so I have this inequality that this is at most that right-hand side there, but let's go back to our system there, right? In my system, I also have the constraints that for every set, the X star of the boundary has to be at least the F value. So when I combine the two, I get that, well, this must be equal to the F value of A intersect B. For A union B, it must be equal to F of A union B, so they're tight. And moreover, theta must be equal to 0. And then when I sort of, so if I put theta equal to 0 there, one can see that that I have this linear dependence between the indicator vectors of these 4 sets, which means that what I can do is, for instance, I can take my laminar family to be A intersect B, and A union B. Okay, so I mean, showing this is is equivalent to showing that, like, for instance, one of these can be written in terms of the indicator vectors of the other sets: A intersect B, B minus A minus B, and A union B. Okay, so that's the main thing, that's sort of this folklore result, as long as F has this weak supermodularity property. Now let's get to the real thing, right? So in our system, we don't have constraints. Okay, so sorry, let me go back to this previous thing, all right? So let's pause for a bit and see, okay, where did we use the fact that we had constraints for all sets, right? So we used it because after arriving at this point, we said that, okay, I also have those inequalities for my sets A intersect B and A union B, or if the other side of the weak supermodularity inequality was the thing that was giving us the inequality, then we would need it for A minus B and B minus A. So we needed the fact that these constraints are there, those opposite constraints are there for all of our sets. And hence we could claim that, well, whichever of these two sides we have attains the max, we get tight sets. And well, if it was A minus B and B minus A, then we would have shown that there are no edges like this. But that's sort of the key place where we use, that's one key place where we use that we have those constraints for all the sets, right? And the second key place is that, well, I mean, we wanted to write, our goal was to write span of, and get a laminar family of sets in our collection, of sets for which we have constraints. And so again, we needed the fact that A intersect B and A union B are in our collection. Now to sort of get that to get this implication really, or actually even that implication, we don't actually quite need that they are in our collection, but we do need the fact that the inequalities for those sets, that the X star of those sets is at least f of s, right? They need not be in our collection, but as long as we can infer that those inequalities are there, are hold for our solution, we'd be okay, right? But the second thing, that we need to write the span of this in terms of the sets in our collection, there we really need the fact that we are looking at constraints in our collection, right? Because that was the whole goal. We want to sort of simplify the structure of the tight constraints to look at only a subset of tight constraints in our collection that have a nice property, this laminar property, right? Okay, so clearly when I go to now only the collection where f of s is at least 3, these two things are going to break, and I'm going to have to do something to sort of correct that. Okay, so now we have just this collection, which I'll call script S. I put labels on some other groups of edges, which we will need. So again, our goal now is, so now we have these tight sets in our collection that cross, and we again want to find a laminar family of tight sets from our collection such that this span properly holds. And we can assume that A union B is not the entire vertex set, right? Just because if that were the case, then like the constraint for A would be the same as the constraint for B minus A, right? And the constraint for B would be the same as the constraint for A minus B, because A union B is the entire vertex set. So then this goal would be quite easy, because we could just take A minus B and B minus A. They're just exactly the same constraints, right? So just a simple case to get rid of. So now I have these tight sets, they cross. So all of these A minus B, A intersect B, B minus A are non-empty. And the complement of A union B is also non-empty. So that was exactly what we needed to utilize this 2A uncrossability property. So I have the stronger inequality, like the same thing there on the right, but with min here. And what that implies is that, well, so as long as both of these sets are in my collection, I can use the previous argument, right? Because that's what the previous arguments needed, that these two sets, like if f of A plus f of B was less than equal to this, and I had constraints for these two sets, then I could, then that's what I was using in the previous argument, that these sets are tight, and I can get this span properly. And I mean, we didn't do the other case in the example, but I mean, if this is what is, if both of these are tight, then again, the sort of folklore result, the M crossing there works for us, right? Okay. So, but the issue is that we may not be in this nice case, right? So it could be, again, we are dropping sets. So it could be that one of these two sets has been dropped and one of that pair of sets has been dropped. But let's make a simple observation first that it can't be that both of these are dropped or both of those are dropped, because what do I have? I know that A and B are in my collection, so their F values are both at least 3, so they add up to at least 6. If a set is dropped, its F value is at most 2. So just the math doesn't work out. I mean, given that I have this, it cannot be that both of these are dropped and both of those are dropped. All right, so where are we? So basically, we have inferred that, well, if both sets are in my collection, from A intersect B or A union B, or from A minus B and B minus A, then we are good. And the hard case is that, and at least one of those has to be in script S. So the hard case is that, or the case that we have to look at is that in both pairs, exactly one of these sets is in S and the other set has been dropped. And let's say from A intersect B, A union B is in my collection, A intersect B has been dropped, that green shaded thing, and from that collection, let's say A minus B is in my collection, but B minus A has been dropped. Right? I mean, there are really 4 cases here, but once you do one case, the other cases are symmetric, right? So let's look at this illustrative case, right? So again, where we are now is that from A intersect B and A union B is in my collection, and A intersect B has been dropped. From A minus B and B minus A minus B is in my collection, and B minus A has been dropped. Okay. Okay, so what are we going to show here? So I claim that, so what we will show is that although the constraints for A intersect B and B minus A have been dropped, they are actually still satisfied. They're not in our system, but we will argue that they are still satisfied. Okay? If they are still satisfied, then we know, as I was pointing out previously, that, so we know that, for instance, if A intersect B is satisfied, I also know that A union B is satisfied. So that means that A union B and A intersect B are tight. And similarly, if B minus A is satisfied, since A minus B is also satisfied, I know that A minus B and B minus A are also tight. So that means that actually all of these 4 sets, A union B, A intersect B, A minus B, B minus A, they're all tight. And we are going to have theta and gamma. There are going to be no edges of that type, theta and gamma. We will actually also show that this implies that there are no edges going between A intersect B and B minus A. All right, so the picture looks a lot cleaner. We just have these kinds of edges. And now if we stare at this picture, we can infer that, well, I can write the edges on the boundary of B. I can get that by taking the edges on the boundary of A minus B, which is in my collection, and then A union B, which is also in my collection, and then I'm double counting this edge here, which is what is the edge on the boundary of A, and so I can subtract that. All right, so that gives me my, if I show this, then I can take my laminar family to be A minus B, and A union B. All of those are in my collection, and I'm good. Right, good. Everyone happy with plan? Yeah.
So your planner family, you're trying to pick a subset of constraints and like just say these are tight and these are like forming a laminar, right? It's not like the other way. You don't have a set of constraint and you're just claiming that this time.
So, I mean, we want to show that we can pick a laminar family of tight constraints that span all the tight cut constraints, right?
Yeah.
And I mean, there is one part that I said, but I'm not sure that if we can show this kind of an uncrossing result, that whenever you have two tight sets, you can uncross and get a laminar family locally for these constraints, then you can actually get a laminar family that spans all the tight constraints.
And do it like globally, because I
Yes.
do that.
Yeah, you can do it globally. I mean, although sort of the cleanest argument to go from here to why you can get this laminar family would be to just say something like pick a maximal laminar family of tight linearly independent constraints and then argue that they must span everything. Because if they didn't, then you could pick a set that crosses it and you could uncross and add something to your laminar family.
So can you repeat why three of those things couldn't something about?
Because f of a plus f of b is at least 6, right? And anything that's dropped has value at most 2, right? And we have that f of a plus f of b is at most f of a intersect b plus f of a in union b, and same thing for the set differences. Okay, all right. So let's see why this is true, right? I mean, this seems a bit magical, right? I mean, it has no business for being true, but it turns out to be true, right? Okay, so we want to show this, right? Now, what I'll actually show is that I want to show this for each set, but let me show it for the sum, right? So let me show that the inequality where we add up these two individual inequality is true. That's what's written as star. I claim that this implies this. Why? Because, well, if I have this star inequality, then at least for one of the sets, I have what I want, right? Let's call that set S. And again, once you have it for a set S, like let's say A intersect B, because A union B is also satisfied, it's in our collection, A union B and A intersect B are going to be tight. Right? So in fact, if I show this, if I know that this inequality holds for one set, then in fact, like say A intersect B, I know that it's actually tight for that set. So this quantity and that quantity are the same, but then that inequality star also implies that it also holds for the other set. Right, so we get this sort of really nice clean thing that as long as you show that the inequality holds, you also get that it's tight, right? And that allows us to get a lot of leverage. All right, okay, so finally our goal is to show that this sort of compound inequality where I'm summing up the x values on the boundary of A intersect B and B minus A is at least f of A intersect B and f of B minus A. Right? And there's one thing that I haven't used at all right now, till now, which is even parity. Right? So somewhere that's going to come into play. Right? So let's see. So suppose this does not hold. So we have this opposite strict inequality there. Then if I sort of look at that picture, that quantity, I'm summing up the edges on the boundary of A intersect B and B minus A. That's the same thing as looking at all the edges on the boundary of B, but then you're also taking twice this alpha, the edges between A intersect B and B minus A. B was tight, so this is the same thing as, this quantity is the same thing as f of B. Right, so what do I get? I get that fb plus 2 alpha is strictly smaller than f of A intersect B plus f of B minus A. Now let's see how can this hold. F of A intersect B and f of B minus A, they're dropped sets, right? So their values are at most 2. So the right hand side is strictly smaller than 4. Or the extreme right side is strictly smaller than 4. So the only way this can hold is if this value is 3. Right? Because there's a strict inequality there. So the only option for this is f of B is equal to 3, f of A intersect B, and f of b minus a is equal to 2. And now Arka spots a contradiction. Okay, all right, but someone should spot a contradiction now.
For disjoint sets, the parity should add up to even number.
So we want to say alpha is 0.
Right, so we'll get to why alpha is 0, but right now I just want to claim that this is a contradiction. Someone in the Zoom answered, yeah, but I think Sipper was also getting there.
The alpha is 1, 5.
So I haven't used the condition yet, right? I haven't used even parity. Right, so even, right, it violates even parity, right? Because even parity says that if I have two disjoint sets, and if I sum up their f values and f of the union, that should be even. Right, so here I have 2 and 2, and f of the union is 3. That violates even parity. Okay, so that's the contradiction. And so to show that star cannot be violated, so this inequality must hold. Again, if this inequality holds, then we know that actually A intersect B and B minus A are also tight. So now we know that star holds, and it actually holds an equality. So we know that this entire thing is an equality. So FB plus 2 alpha is equal to FA intersect B plus F of B minus A. And now I can claim that alpha is equal to 0, because again, the only way of satisfying that constraint is by these values. Right? F of A intersect B plus F of B minus A is at most 4. F of B is at least 3. The only way I can satisfy that equation is, well, if alpha is positive, then the only way I can satisfy this equation is by this choice of values for the sets. And again, that contradicts even parity. Yes.
The K. Then
The even parity condition that was that f of A plus f of B plus f of A union B is even for any two disjoint sets A and B. So it holds for the kth connected spanning subgraph problem and K is even. Okay, and that's the entire proof, right? So we showed that we can uncross these tight cut constraints even when we are restricting it to only include the constraints whose f value is at least 3. That implies we can get a laminar family. And I didn't sort of show the counting argument, the simple counting argument, why that implies an integral edge, but that's fairly straightforward. So let me finish up here. So, right, so we get these nearly tight additive guarantees, cost at mostly LP solution in either K minus 2 or K minus 3H connectivity, depending on whether K is even or odd. And I mean, the variant of this where we only drop set when it's crossed by at least K minus 1 edges gives us, I mean, there we can show that. So actually the same uncrossing arguments work. We don't need to use even parity there, but it's the same sort of, it's the same plan, right? Just that, I mean, at this place we needed, okay, that here is the only set of values, but this contradicts even parity. There the contradiction is even more evident, right? So in fact, it's a bit easier to prove there. But then we can only argue that there's an edge with value at least 2/3, so we get 1.5 times the cost instead of at most the cost. I think I mean, more than those results, I think the sort of what might be of independent interest and the key insight here is that cut constraints can still be uncrossed even after you drop the constraints for some sets that are nearly satisfying. Right? Usually, I mean, cut constraints are a bit fragile in the sense that, I mean, we've sort of been used to thinking about them, that we need to have all of them because we need these constraints for every set. That's what gets used in Ian crossing. And in fact, I mean, in many applications of this iterative rounding, there's some network design component, network connectivity constraints, and some other auxiliary constraints. We usually are careful in keeping all the cut constraints, because otherwise we don't get this laminar structure typically, right? But here it shows that we can sacrifice some of this, right? Still get this nice structure. And some open questions. I mean, sort of there is the obvious open question, right? What if, can we get k minus 1? That's yeah, that would sort of close it. If we wanted to get cost mostly LP solution. I mean, there is another open question which I mentioned earlier, but I didn't put it here, that can we get a feasible solution but better than 2 approximation? And I mean, to get this k minus 1, one would have to do something more than what we do, because you cannot argue that there's always an integral edge if you drop sets. If your rule for dropping is more strict, that you drop only when they're crossed by at least k minus 1 edges. I think there's another sort of quite interesting direction that this kind of line of work opens up. So this is KH connectivity. It's a sort of fundamental but network design problem, but in some sense quite special, that you have like uniform connectivity requirements between every pair of nodes. More general, what about sort of more general connectivity problems? Can you get a similar style of guarantee? By that I mean cost post the optimum, but relaxing the edge connectivity by some constant, additive constant. And that's all I have to say. Yeah,
So for the counting algorithm, you use the fact that it's at least 3. You
Yeah.
say that there are 4 edges,
exactly.
and then you do the simple counting algorithm.
Yeah. Yeah. Yeah.
But it's not true. Like you have a extreme cost solution that if fs is 2 only, then you don't have any equal edge.
Yes,
I think in your paper as well.
it's in the paper. Yeah.
I wanted to ask about that. So that example was about working.
Right. Yeah. Okay. So at the level of, okay, so here is this laminar family where all the f values are at least 3. So where if you wanted to prove that, okay, so all this uncrossing gave us this laminar family, right? As Lapchi was saying, if all the f values are at least 3 in that laminar family, one can argue there's an integral edge. You can't relax the at least 3 to at least 2 and get an integral edge. So sort of that's what that example is indicating. We don't know actually that example can be realized for even k, right? So it is maybe like a simpler task here would be to get k minus 1 edge connectivity for even k. But yeah, we don't know whether that example. So there is an archive paper of this, and there's an example that talks about this tightness here. Yeah, so we don't know if that example can be realized like as an instance of KH connected subgraph with even k, where you get that after picking some integral edges. Yeah, at least I don't think we figured that out yet. Yeah.
The example does not satisfy the parity constraint.
So, I mean, okay, so it depends on how you view the example, right? Because the example just talks about focuses on some sets, those are in the laminar family, right? They need not be just all the nodes in the graph, right? So to satisfy even parity, you would have to add additional nodes, right? And that may or may not be possible. I mean, maybe there is some sort of deeper reason why that's not possible.
That's thanks so many.